Let's consider a detailed analysis of the number system. Complex number is usually denoted by capital letter C. We can also denote complex number using this, or a capital letter C with this. Any is fine in the representation of complex number. Complex numbers have two parts. One is the real part and the other is the imaginary part. The real part of the complex number is usually denoted by capital letter R. The imaginary part will always have an I attached to it, where I is equal to the square root of -1. If you take this square root across, it becomes I squared is -1. We can generally represent a complex number as C, capital letter C, or with small letter z, as x plus I y. This part is the real part of the complex number, and the y is the imaginary part of the complex number. The I attached to this is telling us that this number is an imaginary number. Remember that this I is the square root of -1. We can also represent a complex number with C is small letter z is A plus IB. Both are the same thing, where x is the same as A and y is the same as B. In some engineering textbooks, where I is for instantaneous current, J will be used instead of I, so that not to confuse this instantaneous current with this imaginary number. But generally in mathematics, I is usually used for imaginary numbers. We are going to dedicate the analysis and solution of complex numbers to another video course. Next, real numbers is divided into two. We have rational numbers. Also, we have irrational numbers. For rational numbers, we use capital letter Q to represent rational numbers. And for irrational numbers, we use capital letter Q with a prime or capital letter Q with a complement. Furthermore, rational number is divided into three parts. We have natural numbers. Next, we have whole numbers. And we have integers. Natural numbers can be represented with capital letter N. Whole numbers can be represented with capital letter W, while integers usually represented with capital letter Z. This Z is different from this Z. This Z is a capital letter Z, and this Z is a small letter z. You can see that here we have real numbers, and these real numbers got two families. For the complete video course on this subject, click the link in the description or in the pinned comment section. Rational numbers and irrational numbers. Rational numbers have a family: natural numbers, whole numbers, and integers. And this can be analyzed easily because we can find natural numbers, whole numbers, and integers on the number line. But irrational numbers are very difficult to analyze. And here we can find surds. Usually we say, let's rationalize surds to enable us to reunite it into this family. Mathematicians have tried for decades. The only thing we do is when we get to a certain stage, we leave it as our final answer, which you are going to see in this video course, making sure that we respect all surd laws. Hence, whenever you hear anything like rationalization of surds, remember that surds are irrational numbers, and here we have rational numbers. We are trying to rationalize this into this family. And don't forget that in this family tree, complex number is here. Natural numbers. Natural numbers denoted with capital letter N can be found on the number line. Natural numbers on the number line we consider from 1, 2, 3, 4, 5, 6, and it continues towards positive infinity. Natural numbers do not consider 0 and the negative parts. It starts from 1 to infinity. Next, whole numbers. Whole numbers are usually denoted with capital letter W. Consider the number line. Whole numbers start from 0, 1, 2, 3, 4, 5, 6, and it continues towards positive infinity. Usually on the Cartesian plane, we call this plus x axis. You can see that whole number starts from 0 towards positive infinity. We can say that natural numbers plus 0 is equal to whole numbers. Next, let's consider integers. Integers are usually represented with capital letter Z. Let's consider the number line. Integers considers everything on the number line. 0, 1, 2, 3, 4, 5, and continues towards positive infinity. Also, it considers -1, -2, -3, -4 towards negative infinity. When considering integers, instead of using positive infinity, I can use Z plus, showing all the positive side of the integer. Likewise, I can use Z minus, which is a superscript of minus. This is a superscript of plus. This is representing all the negative part of the integer. You can see that natural numbers, whole numbers, can be found on the number line. Because this is natural numbers, if you include 0, it becomes a whole number. You can see that rational numbers are easy to handle because we can find the numbers on the number line. We usually say that rational numbers can be represented in the form of A over B, and this has 3 definitions, which is number 1, all the numbers found on the number line are rational numbers. That is, on the number line, this is -3 over 1 in the form of A over B. minus 2 over 1 in the form of A over B, minus 1 over 1. Everything on the number line can be represented in the form of A over B, because everything here is like over 1, and it will return back the same value. It continues like this and also like this. This is one definition of rational numbers. Rational numbers have another definition, which states that any two numbers that you divide, for example 1 over 3, will give you a number that keeps reoccurring. This number continues indefinitely. Another example is 5 divided by 9, which is 0.5555, and it continues reoccurring. Another example is 7 over 11, which will give us 0.63636363 and continues indefinitely. Any number that gives us reoccurring numbers is rational numbers. Another definition of rational number in the form of A over B is any division, for example 2 over 5, that is very short and does not continue. Here 0.4 becomes the answer. It's very short, does not have a long value. Another example is 5 over 2, which is 2.5. You can see the answer is very short and did not continue. Another example is 1 over 4, which is 0.25. These are the three definitions of rational numbers in mathematics. For irrational numbers, if we consider 2 over 7, we're going to have, you see, in this division, we have values that are different. When you divide any variable in the form of A over B, and you cannot achieve this, then we say that such number cannot be represented in the form of A over B. That is, if you check the values generated here, they are not reoccurring. They don't have any similarities as they continue. If you consider the square root of 2, you can see that the generated numbers also do not have any similarity or pattern. We say it is a rational number. Same for the value of exponential, for the value of pi, for the value of the square root of 5, and so on. We say that these are irrational numbers. Irrational numbers, just like complex numbers, are very difficult to represent on the Cartesian plane. If you find this video helpful, please click the like button. Also, subscribe for more videos like this. I will see you in the next video.